code walkthrough. So what I want you to do is try to code up this algorithm on your own first. This should be a nice refresher on binary trees. I know it's been a minute since we've done these problems. That's really by design, right? I want to actually force you to do some deep recall right now. And this problem is actually going to be the first in a little mini sequence on binary trees. So definitely give this one a shot on your own first. And if you get stuck, you can find me in the walkthrough video as always. I'll see you there. Hey programmers, Alvin here. Right now let's go over the approach we can use for this flip tree problem. So in this problem we're going to take in a classic binary tree as input. What we want to do is effectively flip the left and right hand branches of this binary tree. And we actually need to apply this recursively. In other words, if we took in this binary tree on the left as our input, what we want to do is have our function mutate and manipulate this existing tree and also result in this sort of structure. Notice what we've done is flipped every left and right pointer. In other words, if I take a look at my root node of A in my input, it of course has a left and right pointer. I notice that the left is B and the right is C. In the output, that A node's left should be C and now its right should be B. Notice how I flipped those two references. This should be the case at every single node. So if I look at the B node in the input, its left is D and the right is E. In the output, the left is E and the right is D. A key thing to remember for this problem is I don't actually want to create a new tree by using new instances of nodes. Instead, I should mutate my tree in place. So how can we go about attacking this one? Well, it's really straightforward looking at the logic we really just described. I think the best way to solve this one is using some recursion. And we know if we use recursion on a binary tree, it would be a type of depth first traversal. So let's say we situate ourselves at the root node. I know that this root node has obviously a left and right pointer. And all I need to do is take those references and swap them. So the right becomes the left and the left becomes the right, just like this. But I need to be sure to apply this flipping logic at every node recursively, which is why I think recursion's a great choice here. So now I root myself at this B node, and again, I swap my left and right. Obviously, to accomplish this swapping logic, we'll want to pay really close attention to make sure that we don't just chop off pieces of our tree. Same thing occurs at the C node, and we do want to swap our null left pointer with our right pointer, which is an F node. That should be the complete logic for us. Bear in mind in this problem, we do want to return the root of the binary tree. So when you code it up, you'll want to watch out for that little nuance. But the complexity of this is really straightforward. We have n as the number of nodes, and then we can say that our time complexity is just O of n. Because we know we're just doing a type of depth first traversal through the tree, so we need a recursive call for every single node of the tree. And within any single call, all we expect to do is really just flip two variables, just doing some variable assignments. The space complexity here is going to be O of n because of the stack space we need to actually perform this recursion. And even if you performed this operation, iteratively, it would still tend to be a space complexity of O of n. Because remember, when it comes to traversing through a tree, you must use some space, right? You're either using some stack space if you have a depth first, or using some queue space if you're using a breadth first. And overall, this would be actually the most efficient way to solve this problem. Alright programmers, so what I think you should do is give this problem a shot on your own. You're going to figure out the code is really, really elegant. And then if you get stuck, you can find me in the walkthrough videos. I'll see you there. Hey programmers, Alvin here. Right now, let's go over the approach we can use for this lefty nodes problem. So in this problem, what we're going to do is take in a binary tree. And what they want us to do is return the leftmost values on every level of this tree. So that means we need to review what a level is. Recall that a level is just all of the nodes that are the same distance away from the root. So for example, if I wanted to look at level 0, that would just be this A node. If I want to look at level 1, that would be the B and C nodes. Level 2 would be the D, E, and F nodes, and so on, right? So there are many levels within a tree. Levels really go across, right? In this problem, what they want us to do is target and return the values of all of the nodes that are on the leftmost side of every level. So that should be all of these nodes. Our output should be an array of these values. So one thing to watch out for this problem is we want the leftmost values on every level, but that doesn't mean that a value we return has to be a left pointer. Case in point would be the I node, right? If you look at the I node's the only node at this level. Although it's a dot right pointer, it would technically be the leftmost node on this level. So I'm still able to return it. What you should also notice is I only should contribute a single node from every level in the tree, because I expect there to be exactly one leftmost node, right? There are going to be no ties here. All right, so let's come up with a high-level strategy for this one. Well, you know you're going to use some sort of tree traversal, and you can actually solve this using either a depth first or a breadth first traversal. I'll sketch through how you can do this with a depth first, right? So we're going to start at the root. And I think no matter which solution you come up with, you're going to need some sense of level tracking. We know that that's inherent to this problem. So what we'll do is we'll say that the root node has a level of 0. And there are a few ways you can actually encode that information in your program. What you could do is just pass an additional argument to track the level if you're doing it recursively, or if you're going to do it iteratively, you can just tag your stack items with this level number. What's great about this pattern is if the root has a level of 0, I know that its immediate children would have a level of 1, right? I just increment that level for my children. We've seen this pattern before, but just to review, in general, let's say you had some small subtree. If the parent node has a level of n, then of course the children have a level of n plus 1. So I can just carry over this logic for every single node of the tree. So if I just plugged in all those values, that would look something like this. In yellow, I have denoted just the level of every node. So how do we actually solve this problem? Well, as we do a traversal, what we should be doing is filling up our output array. We know it's going to start empty. And what I can do is look at my current value as well as the level that it's on. So right now I have a value of A and it's on level 0. If I look at my output array in green, I currently have no value stored at index 0, and so I can go ahead and initialize A into index 0 of this array. Now we have a really important detail to pay attention to. We already made the decision of using a depth first traversal for this. I think we should go a step further and define it as a left to right depth first traversal. In other words, I'm at A right now and I want to go to my left before my right. And that means the next node I visit is the B node, right? And I can apply similar logic to before. So I have this value of B, I find it at level 1, and I currently have nothing stored at index 1 in my array, right? Because A has an index of 0. So that means I can add B to my output. Going depth first again, I go to my left child of D. I currently have nothing stored at index 2, so I take D and put it at index 2. Here's where we get important logic, right? If I was following a true depth first traversal that moves left to right, the next node I visit would be this E node, right? And E has a level of 2. What I'll notice is I already have something stored at index 2. If you labeled the indices of our output array, they would look like this. Because D is already at index 2, I actually don't need to put E inside my output because I already found the leftmost node on level 2. So instead I move to its children like G, right? At this point, I haven't seen anything for level 3 yet, so I go ahead and add G. That gives me index 3 in the array. All right. Next, I travel to this I node. Again, I see a level 4 node for the first time, so I go ahead and add that. And now we see how this logic works out, because the next node I would visit would be H. But I already have an element at index 3, so I ignore it. If I was continuing my depth first traversal, the next node I would visit is actually the C node. But I already have an item at index 1, so I ignore it. And finally, I already have an item at index 2, and I also ignore this final F node. Now, if you look at our output, that actually would be the correct items to return. And so a key insight for this one is if you're traveling depth first traversal left to right, then the first time you encounter a level, that must mean you're hitting the leftmost node on that level. The complexity of this is also great. If we say that n is a number of nodes, the time complexity is simply O of n, right? We're just traveling through every node of the tree once. We'll also say that the space complexity is going to be a linear O of n because we'd be using a stack to do our traversal as well as storing our output array, which at most will have n values on it. So I'm feeling pretty good about the strategy. What I think you should do is try to implement this one on your own. There'll be some good binary tree review. And if you get stuck, you can find me in the walkthrough video. I'll see you there.
Mission at 30 minutes remaining. Allied destroyer joining.
Hey programmers, Alvin here. Right now let's go over the approach we can use for this can color problem. So in this problem, what we're going to do is take in a graph as some input. Do bear in mind that we're going to be given an undirected graph. So what does that mean? To review, an undirected graph is a graph where if we have an edge between two nodes, for example, an edge between E and A, that means I can travel in either direction. So I can travel from E to A, but also from A to E. What we want to do here is actually return true or false, indicating whether or not we can color the graph using two different colors. And the rule is we must alternate colors. And that means if two nodes are neighbors, they must be different colors. So I'll approach this one visually for now, just to make sure we understand this problem. So I'm going to choose two arbitrary colors. Let's just say red and blue. So let's say I wanted to color this E node. I'll just make it red. And if I make E red, that means its neighbor, that is the A node, must be blue. And this pattern carries on further, right? Now that I've made A blue, its neighbors of B and C must be red. And finally, this D node must be blue, right? Because its lone neighbor of B is red. So bear in mind, if we take a look at this graph right now, I have every node colored, and it does obey the rule that I always alternate colors, right? For every single node, it's going to be a different color than its immediate neighbors. Because it's possible to color this graph in such an alternating way, we should return true for our function. So at a high level, let's take a look at some other possibilities. Let's say I gave you this graph of 3 nodes. Let's say you start a similar approach. Just arbitrarily, I'm going to choose one of my colors to color the H. Let's say I chose red. So if H is red, I can look at a neighbor like I, and I'll have to make that one blue. At this point, I still need to color the J node, but there's no color I can choose here such that I avoid putting 2 colors adjacent next to each other. So this would be a case where I return false, right? We can't color this graph with 2 different colors. So something I'll bring up right now is you might have the instinct that, all right, this graph is going to be not possible to be colored because we have a cycle. That happens to just be a coincidence, meaning there are some types of graphs that have cycles, but we can still color with 2 different colors. So let's say we took a look at this example. How would we go about coloring this graph? It would actually be possible, so we should return true. Just make Q and T one color, and then S and R different colors. Now you still satisfy the constraint that we're strictly alternating our colors. So simple cycle detection won't be the way to solve this one. Let's come up with a strategy by looking at a larger example. So let's say that this was our graph. Notice that this input graph actually has like 2 separate connected components. So that means we're going to need some, piece of code that actually can leap and begin a traversal at these disparate regions, right? And what we can do is solve this one using a depth-first traversal, right? And what we'll want to do is kind of modify that and implement some of that island hopping logic, which we've seen many times in the course. So what I'll do is I'm just going to list out my different nodes in the top right, because we're going to begin with some iterative code, right? I'm going to begin iterating through every node, and it doesn't matter the order that I iterate through these nodes, because I'm going to begin a depth-first traversal starting at that node. So let's say the first node I iterate through is the A node. So I'm going to start the A node, and here's where I begin my recursion, right? What I should do is notice that, all right, the current node that I'm on right now of A, it is not colored, right? If it's not colored, that means it's also not visited, right? If I implement this algorithm in some code, of course, we're going to do classic things like use, hash sets as well as maybe objects to store this coloring and visited information. Since A is not visited yet, I should color it for the first time. Let's just say I arbitrarily choose red to color this one. Cool, so now that I've chosen red for my A node, I need to visit its neighbors, right? If I did this in a depth-first order, let's say I was visiting the B node next. If I visit B, I know to choose the opposite color for my next recursive call. So right now I'm red. When I visit B, just flip that to blue. Right. In a similar way, when I need to travel to the other neighbors of A, they're all also going to be considered as blue nodes. So I is also going to be blue. If I was truly doing this in a depth-first order, I must travel deeper down this path and hit the H. Right now, my color is blue, so I should flip back to a red over here. Right. And finally, when I do some backtracking for the A node, A still has 1 neighbor to visit, and of course I color them blue. And when it comes to designing the logic that helps us flip back and forth between our 2 different colors, I can really just use some Boolean data to represent that, right? Maybe like true represents red and false represents blue. So that's really easy to code up. At this point, I actually get to return from this recursive call, right? I can't explore this island any further. So here's where I fall back to my iterative code. Right, so now I look at the B node in my iterations, and I can check that B is already visited, right? If it's colored at all, that means I already visited it. And so I don't need to begin a traversal at that node. Instead, I go to the next iteration and look at C. Since C is uncolored, that means it's not visited, so I should begin a new depth-first traversal. Like before, whenever I start my recursion here, I'm going to just begin with a red. So I color the C node as red. And by depth first, let's say I visit my neighbor, I'm going to color D as blue. Next iteration, I should travel to the J node, and I should color that as red, right? Because on my next recursive call, I take the opposite color. Nice. And at this point, J still has 1 edge that I can use, so I travel from J to C, right? And at this point, when I transition from J to C, I'm going to want to color this node blue, but I can see that it's already colored and it's colored red. So that would be a contradiction, right? I want to color it blue right now to satisfy the constraints of the problem, but it's already colored as red. And so this is actually a bad scenario. What I should do is return false, right? If ever I travel to a node that I've seen before and it's a different color than what I intend right now, then I can return false. It must be not possible to color this graph in an alternating pattern. On the flip side of that, if I travel to a node I previously colored and it's already the same color that I intend right now, then things are okay and I can continue my traversal returning true. So we talk about the complexity of this algorithm. We know that if n is the number of nodes, we're really implementing just a little variation off of our classic depth-first traversal, right? So bear in mind that if I had a graph of n nodes, the number of edges that I could possibly have in the worst case would be n squared. And I know that my depth-first traversal is going to travel through every edge. So for that reason, I'm going to say that my time complexity is O of n squared. And you can also probably consider this as O of e, where e is the number of edges, right? A few ways to interpret this one. The space complexity here is also going to be O of n because of course I need some stack space to do this recursion, and to store this like coloring information and what nodes we visited, we're probably either going to use like a hash set or some type of stored data structure. Alright programmers, so I'm feeling pretty good about this one. What I want you to do is try to code this one up on your own, kind of refreshing those nice graph patterns, and if you get stuck you can find me in the walkthrough videos. I'll see you there. Hey programmers, Alvin here. Right now let's go over the approach for this tolerant teams problem. So in this problem, what we're going to do is take in an array containing rivalries as input. So a single pair here represents a rivalry. Notice that a rivalry is really just going to be given as two strings, right? So consuming the very first pair of rivalries here, we can say that Philip and Seb should not be placed on the same team. In a similar way, Raj and Nader should also not be placed on the same team. So the first thing we want to do is understand that this problem is really just a graph problem. So what we want to do is start by visualizing every person within our list as a node of a graph. And then from there, I know I can encode edges as a rivalry between two folks. In other words, since Philip and Seb should not be on the same team, I'll put an edge between them, and likewise I'll add another edge for Raj and Nader. So now that I have actually described this problem in terms of a graph structure, what do I want to do with it? Well, the problem asks you to figure out whether or not you can divide the people into two teams such that rivals are not on the same team. And the teams we create can be of any size, meaning they don't need to be equal sizes. So what's some intuition we can use to solve this one? Well, let me start by applying some arbitrary team to Philip, and I'll just apply him to the red team. Then from there, if I make Philip on the red team, then Seb must be on the opposite team, right? Because they're rivals. Seb cannot be on the red team, which means he must be on the blue team. In a similar way, I just want to make sure Raj and Nader are also on separate teams, so they should be two different colors. Now, really what we described here is really just a graph coloring. What we want to accomplish is adjacent nodes within our graph should always be different colors. In other words, I can't place a red node next to a red node, and likewise, no blue nodes next to blue nodes. We covered this graph coloring algorithm previously, and to bring in some more terminology, we call this a bipartite graph. Meaning we can split our graph into two parties, right? One red party and one blue party, such that adjacent nodes are not the same color, right? They're members of different parties, or in this problem, different teams. So let's go over another example here. Let's say I gave you some rivalries that created this graph structure. Let's say we tried to split up into two separate teams using our graph coloring algorithm. You can begin your traversal at any particular node here. Let's say I start at Nader, and I arbitrarily color Nader as the red team. From that point, I go to a neighbor, so Raj, and I must alternate the color, so I make Raj blue. Then I go to Philip, let's say. I must make Philip red, just flipping the color. Then I go ahead and make Seb blue. And at this point, there's actually one more edge we haven't traveled through yet, and that would be the edge between Seb and Raj. Right now, Seb is blue. When I travel to Raj, I would like to make that node red, but right now it's currently colored as blue, which means I have a contradiction, right? And just looking at the space of our graph, we see that Raj and Seb are both blue, and they are neighbors. So this would mean it's not possible to separate our input into two separate teams. So this is a scenario where we should return false. What you'll also want to worry about in this problem is, depending on the rival information they give you, you could actually construct two separate disconnected regions of graph, right? So this is technically one giant graph that has two separate islands. So when you implement this code, you'll want to do a depth-first traversal with some island hopping logic. In other words, let's say you started traversing at Betty. You know you're going to make a single pair here represent a problem. So in this problem, what we're going to do is take in an array containing rivalries as input. So a single pair here represents a rivalry. Notice that a rivalry is really just going to be given as two strings, right? So consuming the very first pair of rivalries here, we can say that Philip and Seb should not be placed on the same team. In a similar way, Raj and Nader should also not be placed on the same team. So the first thing we want to do is understand that this problem is really just a graph problem. So what we want to do is start by visualizing every person within our list as a node of a graph. And then from there, I know I can encode edges as a rivalry between two folks. In other words,